Ja, grüß Gott und ein ganz herzliches Willkommen hier heute Nachmittag zur Lise-Meitner-Lecture 2025. Diese Vortragsreihe wird seit vielen Jahren von der Deutschen Physikalischen Gesellschaft und der Österreichischen Physikalischen Gesellschaft veranstaltet, um einmal im Jahr eine bedeutende Wissenschaftlerin in der Physik auf die Bühne zu holen und ihr die Gelegenheit zu geben, in der Öffentlichkeit wirklich nochmal genau zu erzählen, worum es in der Forschung geht. Ich, wie gesagt, darf Sie ganz herzlich begrüßen hier heute an diesem Nachmittag, trotz des sommerlichen Wetters oder vielleicht gerade wegen des schwülwarmen sommerlichen Wetters, habt ihr den Weg hierher gefunden. Das freut mich sehr, freut uns alle hier sehr. Mein Name ist Roland Wester, ich bin Experimentalphysiker hier am Institut für Ionenphysik und angewandte Physik der Universität Innsbruck und werde jetzt kurz noch was zur Einführung sagen und dann werden wir gleich übergeben. Zunächst mal freut es mich sehr, die Vertreterinnen und Vertreter der DPG, der Deutschen Physikalischen Gesellschaft, und der ÖPG, der Österreichischen Physikalischen Gesellschaft, hier begrüßen zu dürfen. Namentlich Barbara Sandow, Agnes Sander, Michaela Lemmer und Erich Runge für die DPG, hier vorne in der ersten Reihe. Herzlich willkommen. Und für die ÖPG Präsidentin Alberta Bonani und Vizepräsident Christian Teichert hier ebenfalls in der ersten Reihe. Herzlich willkommen. Ich darf übrigens sagen, wir sind nicht nur hier im Saal versammelt, hier im Audimax des Agnes-Heller-Hauses der Universität Innsbruck, dem größten, neuesten und wirklich, wie ich finde, wirklich wunderschönen Hörsaal, der erst seit wenigen Jahren, ich glaube 2, 3 Jahre jetzt eröffnet ist, sondern wir streamen auch live auf YouTube über die Seite, den YouTube-Channel der Deutschen Physikalischen Gesellschaft und ich begrüße also auch alle, die online zugeschaltet sind zu dieser Lise-Meitner-Lecture. Als Vertreter der Universität Innsbruck möchte ich ganz kurz auch noch Vizerektor Gregor Weiß, Vizerektor für Forschung, begrüßen, stellvertretend für das Rektorat der Universität und ebenfalls Experimentalphysiker. Herzlich willkommen. Ja, und da diese Veranstaltung und dieser Vortrag heute auf Englisch stattfindet, werde ich jetzt ins Englische überwechseln. I will switch to English. And just say one statement about Lise-Meitner, who is giving her name to this lecture series. Lise-Meitner was one of the most influential physicists of the 20th century. And I would say it would not only have been an honor for her to have received the Nobel Prize in Physics, which unfortunately she never did, but I would actually say it's rather the opposite. It would have been really a distinction for the Nobel Prize to have her in the list of awardees of the last century. It never happened. Nevertheless, today Lise-Meitner is clearly not forgotten, but rather is commemorated in various ways. Among them in this lecture series here. This Lise-Meitner-Lecture series here. I will not say any further words, give the word over to my colleague, Professor Monika Ritsch-Marte, who will now introduce Anne Jullier, our speaker of today, to you.
A warm, if not to say today, a hot welcome from my side also. As you already heard, it's my pleasure to introduce Anne Jullier to you. But before we do this, just very quickly, one word or 2 words on the Lise-Meitner lectures. This is already the 16th Lise-Meitner lectures. It all started in 2008 as a joint project of the Austrian and the German Physical Society. It was the joint idea of Barbara Sandow and myself to bring to you a series of talks of female physicists. And you can see it started all in 2008 with Millie Dresselhaus from MIT. And if you take a quick look on how many very great talks we have had on various topics, you can see that it has a little bit of a tradition already. You can't do something like this with it at least showing one picture of Lise-Meitner. So this is a very famous one. As I already said, what we want to do is we want to show and demonstrate to you how many really cool women physicists are around, and to showcase that, to highlight it. And with this, I skip to introducing to you today's Lise-Meitner-Lecture, Professor Dr. Anne Luyet from Lund University in Sweden. Her career started in Paris, where she did a master's in theoretical physics and mathematics at the Pierre and Marie Curie University. But then she thought she'd rather switch to experimental physics. So basically, she decided to work on laser physics, and in particular on multiphoton ionization in high-intensity laser field. This was done near Paris at the Commissariat à l'énergie atomique et aux énergies alternatives, CEA. And there she also got a permanent position a little bit later in 1986, her first permanent position. She did in between a few postdocs, and I would like to mention Chalmers Institute of Technology in Gothenburg in Sweden, as well as at the University of Southern California in LA, in the US. But then in 1992, she decided to move to Sweden, to Lund University, and has been a professor there since 1997. She has received a multitude of awards and recognitions. And for example, after the world record for the shortest laser pulse, 170 attoseconds, in 2003, she became a member of the Royal Swedish Academy in Sciences in 2004. She also won the very prestigious UNESCO L'Oréal Award in 2011. And among other things, the Wolf Prize, which, as you might have heard, is very often a precursor. If you are probable to gain the Nobel Prize, very often have also gained the Wolf Prize. Then it was finally the most recent and most prestigious award, the Nobel Prize in Physics in 2023, together with Ferenc Krauss and Pierre Agostini, for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. And with this, and not much more ado, I'd like to hand over to you, and first of all, also thank you for taking the time to come here and give this talk to us. Thank you.
Thank you. Thank you very much. It's a real pleasure to be here and to talk about attosecond pulses, to give this Lise-Meitner lecture. Actually, I got a Lise-Meitner award in Sweden like 5 years ago, and it was just for the history thing. It was in Gothenburg, and after that we went to the house close to Gothenburg, a little bit north of Gothenburg, where she spent some time, Lise-Meitner, as you know. And the story says that there is a mountain, not the Alps, but a small mountain just beside this house, and this is where she went skiing, cross-country ski in Sweden, and had this idea about nuclear, not fusion, fission. Yes, thank you. I don't know if this is really true, but this is the story about it. Okay, so now I switch subject. I'm going to talk about attosecond pulses of light for the study of electron dynamics. Just to introduce the subject, this is a kind of arrow of time, orders of magnitude. If you don't know what is an attosecond, you have at the top 0 point and then 7001. It's a very short time. And here you have starting by the age of the universe, which is roughly 10 to 18 seconds, and down to the attosecond, 10 to minus 18 seconds. So you can say that there is the same difference between 1 second and the age of the universe done from attosecond to 1 second. So you have different time scale of humanity, astronomical time scales, and then at the bottom, mechanical time scale, electronic time scale, femtosecond time scale. This is the time scale of the motion of atoms in molecules. And then attosecond, it's the time scale of electron motion in atoms. Looking at atoms moving in molecules is what we call femtosecond chemistry. And this was awarded Nobel Prize in Chemistry 1999 to Ahmed Zival. And to generate attosecond pulses and to use it, as was mentioned in the introduction, led to a Nobel Prize in physics. Sometimes this is called attosecond physics, a little bit following femtosecond chemistry, to Pierre Agostini, Ferencross, and myself. So this is the outline of the talk. It's a very general talk. Only in the end I will become a little bit more specific. First, give you a background of this research field. Then I will talk about high-order harmonic generation, attosecond light pulse, and what we do with this pulse, a study of electron dynamics. Let me start by really the background of the field. And I would like to start with the invention of the laser, 1960, by Theodor Meinmann. You have a picture of one of the first lasers, ruby laser. And this is really thanks to a discovery, theoretical discovery by Albert Einstein, 1916, the discovery of stimulated emission of radiation, which itself really follow the discovery of light quanta by Max Planck in 1900, which really started the revolution of quantum mechanics. The invention of the laser led to new research fields. One is nonlinear optics, and here you have an experimental setup of the first experiment showing second harmonic generation. Let me try to use this. I hate that. Oh, this doesn't work. Okay, I will use my hands. So what you see is a ruby laser focused into a piece of quartz. You analyze the radiation. Yeah, now it's, yeah. Yeah. I like laser pointer, of course. Or sticks. So I use my hands, okay? So here you have a prism to analyze the radiation, and then you have a photon detector. And you can see 2 points on this detector, the fundamental field and then the second harmonic. So in this process, there's really new frequencies which are being generated, in this case, second harmonic. Another field that was that started thanks to the invention of the laser is atoms in strong laser fields, multi-photon processes. Here you have a picture of 2-photon excitation by absorbing 2 photons. And this was actually predicted in 1931 by Maria Goeppert-Mayer at the beginning of quantum mechanics. An atom can also absorb several photons and be ionized. This is called multi-photon ionization. It was pioneered by Russian scientists in the 60s. In 1979, Pierre Agostini and his group in Paris discovered the phenomenon of above-threshold ionization, where an atom absorbs more photons than needed and is ionized. And you can detect these processes by looking at the energy of the electrons that are being emitted. My own thesis work, this was the beginning of the 80s, was to look at multiple ionization processes by multiphoton absorption. Here you have some picture of doubly ionized xenon, doubly ionized by absorbing many photons. So at this point, it was clear that in this multiphoton absorption, probably we create excited atoms or excited ions. Would be very interesting to look at the fluorescence emitted by these excited atoms or ions. So this brings to the second part of this talk, high-order harmonic generation. So we set up an experiment. We are in 1987, looking very much like the first experimental setup that I showed you. An intense laser focused not into a piece of quartz, but into a gas of atoms. And then we have a grating to analyze the radiation and a detector. This is a picture of the laser that we were using at that time, neodymium YAG laser, 1 micrometer wavelength, 40 picosecond, 10 Hertz repetition rate. This looks extremely old for those using laser, but at the same time it's very pedagogical because you see the laser cavity, you have two mirrors, and then the oscillator in between, and then you have two amplifiers. What did we see? We did not see fluorescence, and that's the beauty of experimental physics, is sometimes you see unexpected results. We saw high-order harmonics of the laser field. Here you have one of the first spectra obtained in argon gas, and what you see here are odd high harmonics of the laser field, starting with 13 and ending with 31. And what was really interesting is that when you plot the distribution of these high harmonics, you see a first decrease and then a plateau, and it ends with a cutoff. And I would like to say that the plateau was really the new result in this experiment. The reason was that at that time, we were thinking very much in terms of perturbation theory. And if you use a perturbation theory approach and expand the polarization in the medium in terms of powers of the electric field, you assume that the first order must be much larger than the third, much larger than the fifth, etc., for this series to converge. And this was not the case with this very long plateau. Let me stress that we only have odd orders, and this is because of the symmetry of the interaction, symmetry with respect to the center of the medium, which kills the even order harmonics. If we look at what is the photon energy of these harmonics, this is a picture of the electromagnetic spectrum, starting from the radio waves to the X-ray. So we start in the infrared, but then you multiply by a high integer. So we are typically in this extreme ultraviolet region of the spectrum. So in this region, light is invisible to eye and is strongly absorbed by matter. So it interacts a lot with matter, which makes it interesting. Just if some of you are not physicists and harmonics is a difficult concept, I'm sure you know about harmonics in music. And actually, when you play music instruments, and in particular string instruments, you produce not only a certain tone, but many harmonics. And the number of harmonics is what makes the clang of music instruments. So we have similar phenomena in both cases we have a strong interaction. In our case, between atoms and intense laser pulse, and in music, between here the string over the violin and the bow, leading to the emission of this high order harmonics. Of course, music, we talk about acoustic waves, and now I'm talking about light waves, so very different type of waves, different frequencies. Another easy slide here, we are talking about coherent light, not incoherent light, like everywhere around us, where atoms emit waves in all directions and at any time. We are talking about laser light type of emission, where atoms, actually in order to have a macroscopic field, we need to have a coherent buildup of the radiation in the medium. So we need a certain phase matching condition to be realized. We need that all of these atoms emit waves that are in phase. Another small analogy with music here, you can imagine that you have a conductor here, and what is on the left is the orchestra that is playing, that is what orchestra does before the concert, and on the right is when the concert has started, the musicians play together. It's maybe not perfect analogy, but it's just to give some images. A little bit more physics here. What, as a young scientist at the time, I found very fascinating is that to understand this process, you need to do both atomic physics or quantum mechanics and nonlinear optics. So you need an atom to produce all of these harmonics. This is described by Schrödinger equation that you have here with an atomic potential, a laser-atom interaction, which we can write in the dipole approximation, with a classical field, our laser field. But you also need to consider the response from the whole medium. This is described by a Maxwell equation, which can be simplified to a wave equation as written here, with a field which is generated due to a polarization in the medium. And actually the first attempts to understand this process of high-order harmonic generation were done by numerically solving both equations. With good success, however, we missed the physics behind. So the physics actually came a little bit later, as I'm going to show you. 92, progress in instrumentation. You see here myself, a long time ago, with my first PhD student, Philippe Balcoud. We are building an instrument dedicated to the generation and study of high-order harmonic generation. This instrument includes more or less what I already mentioned. You don't see the laser, it's behind the wall. You see the lens, then there is a gas jet, then there is optics in the middle chamber to analyze the radiation, and finally a photon detector, which in this case is an electron multiplier. Also progress in laser technology with a nice discovery that led to a Nobel Prize to Gérard Mourou and Donna Strickland in 2018, which is the chirp pulse amplification. It's a technique allowing to amplify a short laser pulse. And together with a new laser medium called titanium sapphire, really new lasers, really much better to study high-order harmonic generation. And for example, in Lund, at the Lund Laser Center, they built one of these laser system, terawatt laser system, using this new technique, chirp pulse amplification. And this is also the beginning of a European collaboration pushed by the European Union So we collaborate with the Swedish scientist behind this laser. We bring the instrument that you have seen to Lund to do experiments. And this results in me moving to Lund, not really because of a laser, because of a private reason. A little bit later, I moved to Lund, 1994. I became associate professor in 95 and professor in 97. I'm coming to the third part. You follow me? Yes? Which is called attosecond light pulses. So attosecond light pulse is an idea that was proposed just a few years after the discovery of the high-order harmonics. And it's illustrated on this cartoon. So what you have here are 3 harmonics. So these are 3 waves, slightly different frequencies. So now let's assume that these 3 waves are phase-locked. In phase, they are synchronized at a certain time. That means that the maxima happen to be at the same time. Because of the periodicity of the process, after 1 or half a laser period, the minima will be at the same time. Another half laser period, the maxima again at the same time, etc. And now if you sum these 3 waves, you can do that in your head. We get a train of attosecond pulses, a train of short light pulses, simply because of interferences. When these harmonics are synchronized, we have constructive interferences. When they are not, we have destructive interferences. This is very similar to diffraction via multiple slits. Here, our slits are not in space, they are actually in time, so you have a series of slits in time. So if you plot the intensity of these pulses, you obtain this series of very short light pulse. And half a laser period with this titanium sapphire laser is 1.3 femtosecond, which means that here we are below femtosecond. As soon as we are below femtosecond, we call this attosecond. So we are not talking about a few attoseconds, we are talking about a few hundred of attoseconds in all of this physics. Now, if you sum not only 3 harmonics, but let's say 10 harmonics, and if they are still phase-locked, you can get even shorter pulses. So this was very exciting. The question was, are the harmonics phase-locked? And it's going to take us 14 years to really be able to answer to this question. So the answer is yes, in some conditions. And yes, not really, but almost in some conditions. So let me go through a little bit these 14 years very quickly. What happened? First of all, so far I've mainly talked about experiments, but now theorists helped the field in proposing a very nice intuitive picture of the interaction between an atom and a strong laser field, which is represented on this cartoon. So what is shown here is the atomic potential. Normally it looks like this, the Coulomb potential in the simplest case with a revolution symmetry. But now you have this strong laser atom interaction, and this laser atom interaction is going to distort the potential in one direction of the laser polarization, which is linear polarization. And that makes possible for an electron in the ground state to tunnel through this potential barrier. Then the electron is driven away by the laser field. Is a field, this is a wave, change of sign, the electron is driven back, and there is probability for the electron to recombine back to the ground states. So it's an interference process here. It's a quantum mechanical process where you have a part of the wave function going out, coming back. interfering back. And in this process, you have emission of a short light pulse. So now I have an analogy to this picture, which I'm not sure I'm going to dare to show to you, but okay, let's try. So you can take this as a small parenthesis, and it's called The Adventure of an Electron in a Laser Field. And it's in Swedish, but it's not so difficult. You remove the C and you put some K. And you can represent it like this. So this is an electron in a prism. The electron in the ground state is strongly bound. That's good, otherwise we would not exist. And on the side is a roller coaster. Okay, so the electron sees this roller coaster and would like to have fun. What does the electron do? It escapes, yes. How? Tunnel, yes. You are very good in Innsbruck. That's a right answer directly. And sometimes I get a long time to get the right answer. So this is what the electron is doing. Then everything is very nice. The electron has fun. Is driven by the laser up and down. This story is finishing very bad. And this is the end of the story. The electron is meeting on its trajectory this open prism. This is the ion, and fall into the prism. And in this fall, its energy is, you can say that it's screaming out its energy. And this is our attosecond light pulse. End of the story. Yes. So now this, what I just told you, is actually repeated every half laser period on each side of the atom. You see this symmetry property of the interaction. So what is shown here are these electron trajectories that are repeated every half laser period, leading to the emission of a train of attosecond pulses with actually a spin flip between consecutive attosecond pulses. And now if you go to the frequency domain, Fourier transform, you go to the frequency domain, what do you get? You get a comb of harmonics, and actually odd order harmonics. This is related to the spin flip between consecutive attosecond pulses. So how do we understand this plateau? This plateau is actually understood in the time domain by the emission of a short light pulse. So this emission of a short light pulse, frequency domain, leads to a broad distribution of harmonics. So now we have an intuitive time domain description of the interaction. Now I'm only talking about the single atom interaction. During that time, also progress in understanding phase matching, how does it work? If you want to phase match a nonlinear optical process, you have to make sure that the refractive index of the light that is generated is equal to the refractive index of the fundamental light. The phase velocity of the two fields driving generated needs to be equal. Let's look at the variation of the refractive index as a function of frequency. The refractive index of the laser is larger than 1. We are in the visible infrared region, near infrared. Refractive index of these harmonics are less than 1 in this region. So it doesn't work. Fortunately, at the same time as we have this harmonic generation process, we have also ionization of the medium. Some of the electrons, they don't come back. The electrons have fun in this roller coaster forever, okay, or at least during some time. So that at the same time as we have this, we have also partial ionization of the medium. And if we account for this and calculate the refractive index at the fundamental frequency, you had an additional term, which is written on the right, negative term, that lower the refractive index so that you can achieve phase matching. So in other words, there is some kind of magic phase matching happening in this process. There is ionization of the medium. You only need a few percent of the atoms to be ionized for this to happen, and then you have this phase matching. This also tells us that there is really a window of laser intensity when we have this phenomena. The intensity needs to be strong. We talk about 10 to 14 watts per square centimeter in order to have this strong single atom response, but not too high, because otherwise we ionize too much the medium and phase matching is ruined. This is the simple picture. In reality, I just mentioned that for the expert in the audience, that you also need to account for the influence of focusing the radiation as well as the electron trajectory. But the main effect is this neutral atom dispersion and the influence of the ionization. Now I'm coming to 2001, so this is the end of these 14 years. We have learned what is happening more and more, but still it was very important to measure attosecond pulse, and this was realized by my two colleagues that got the Nobel Prize together with me, Pierre Agostini and Ferencváros. Ferencváros managed to produce isolated attosecond pulse and measure them. Pierre Agostini measured attosecond pulses in a train of pulses. I'm not going to describe their technique in details, just to give you the principle. I will come back to Pierre Agostini's method a little bit later in connection with application. So basically the idea is to do a cross-correlation experiment. These are very short time. There is no detector. So how can you measure the duration of these light pulses? What you can do is you can measure this light pulse in correlation with actually the optical wave that is generating the pulse. So it's a cross-correlation between this optical wave and the attosecond pulse. What is measured is the ionization of a gas, and electrons are detected. So let me try to explain to you the idea with my hands. So here is one attosecond pulse that you want to measure, and here is the optical wave, okay, used to generate this attosecond pulse. And now we ionize a gas and measure electrons as a function of the delay between these two fields. Okay, we vary the delay between attosecond pulse and this optical wave. And what we measure depends on whether we are here or here. I don't know if you see the difference. Yes. Now, if this pulse is not very short, but long, like this, when I do this, I see no difference. So the shorter this pulse is, the stronger this cross-correlation signal is going to be. So this is the principle for the method, which was realized in 2001, approximately at the same time, both in Paris and in Vienna. And then here you have a few results in Lund, in Milan. And the present record of the shortest pulse is 43 attoseconds, and this obtained in Zurich. I put a little European flag here. It's a little bit political comment here. I think the reason why attosecond science has been so strong in Europe is because we have been a small community. This is not the case anymore now, but at least in the 90s and beginning of 2000, we were a small community. We were a part of European networks and meeting every half year or so, exchanging results, students, and so it's a strong and really together community. So I think it's one reason why Europe is so strong in this field. This is the end of my political comment. Okay, and I would like to finish because I showed you a very old laser and actually an old instrument. This is how it looks like now at the Lund Laser Center. It's an example of the laser that we use. It's based on optical parametric amplification. And then the type of instrument that we use, simply a vacuum chamber. Okay, I'm coming now to the last part, which is a study of electron dynamics. What do we do? I'll start by a quote by actually Werner Heisenberg. Now is the anniversary of the quantum science and technology. And this is a quote from Werner Heisenberg. The formal, already in 1925, he had worries, and this is what he writes here. The formal rules which are used in quantum theory for calculating observable quantities may be seriously criticized on the grounds that they contain as basic element relationship between quantities that are apparently unobservable in principle. And I'm going to address this wave function. Can we measure the wave function, not only the probability square, but the wave function, its phase and amplitude? Can we look at the time evolution of the wave function? And this is what we try to do with our attosecond pulse. I'm going to concentrate on a simple process, which is photoionization of atoms, which is shown here. This is the photoelectric effect, but on a simple atomic system. And well, Einstein interpreted the photoelectric effect thanks to the light quanta, as you know. And this led to this duality of light, both in waves and particle. But now I'm going to concentrate on the photoelectron coming out. And I'm sure you think of this photoelectron as a particle coming to a detector. Click. You can measure its energy or its momentum. But this photoelectron is also a wave. So can we measure its wave properties? This is the question I'm going to address a little bit, how long time it takes for an electron to be emitted, and what are the wave properties of a photoelectron. And toward the end, I will even touch what are the quantum properties of the photoelectron. How do we do that? Well, our tool are this train of attosecond pulses. In the frequency domain, this is our harmonic comb. If you use this to photoionize an atom, as shown on the right, you are not getting any temporal information or phase information. You just produce electrons, and you can measure their energy. So you don't learn anything new. So our tool is actually the combination of this XUV light and, again, the optical wave that is used to generate this light and represented in the time domain and in the frequency domain. So thanks to this optical wave, this laser feed, now we can produce two photon ionization processes, as shown on the right. You can absorb one harmonic. This is where I would like to have a pointer, but no. Yeah, you can absorb one harmonic and then a laser photon, or you can absorb the next harmonic, and then you can have stimulated emission of a photon. So these sideband peaks can be reached by 2 quantum paths. We have a quantum interferometer. The signal that you get is going to depend on the sum of the amplitude of 2 quantum paths. Is going to depend on the relative phases between the 2 quantum paths. How is done in practice? So the technique, so now let me say one more thing. In order to, if you want to look at interferences, you would like something to vary. And what will vary is the delay between the attosecond pulse train and the optical wave. This technique has been actually used by Pierre Agostini. It was invented by a theoretical group, 1996, and used by Pierre Agostini to measure the pulse duration of attosecond pulses in a train. It's called RABBIT, like reconstruction of attosecond beating by interference of 2-photon transition. And here we follow tradition from ultrafast optics to use diagnostic techniques with animal names. So maybe you have heard of their techniques like frog, spider. This is called rabbit. And that's the reason why. How it's done in practice? We need an optical interferometer. We separate our laser into 2. In one arm at the top, we generate high-order harmonics or this attosecond pulse train. We remove the fundamental field with a metallic filter. And then we have a probe arm. This is a Mach-Zehnder interferometer with a delay stage. In practice, the size of this interferometer is like this. It has to be very stable, and we spend a lot of time with active stabilization technique to make it stable on the attosecond level. Then we send both radiation into a chamber where we photoionize and we measure the electrons. This is what we get. This is called a rabbit spectrogram. So what you see is a photoelectron spectrum as a function of delay. You see what we call main bands, which are due to absorption of harmonics only. And the interesting information is in these side bands that you see in between. Now, these side bands nicely oscillate with a period of oscillation which is 1.3 femtosecond. And the information is really contained in the phase of this oscillation. You can represent that on a clock. We're measuring time, so it's nice to talk about clocks. 1 hour on this clock is half a laser period, so this is 1,300 attoseconds. We can measure an arrow on this clock very accurately within tenths of attosecond. However, we don't know what this arrow is, but we can follow how this arrow is varying. For example, we can follow one sideband to the next, what is the difference of phase between these 2 oscillations. So what we measure is really a phase variation, or if you want, a delay. We don't care about an absolute phase in these measurements. What we want to know is the spectral phase variation or group delay. So we are measuring group delays. So now let me take an example. So we look at actually an old problem which was studied using synchrotron radiation in the 60s. This is photoionization of xenon atoms in the 4D shell. And what you see here from 60 to 140 eV is a beautiful resonance. It's a broad resonance. This is called a giant dipole resonance in xenon. It has been interpreted in terms of collective effect in the 4D shell. But now we are very ambitious. We would like to know what is happening, to do what is the electron dynamics in such a process. So this is what we want to do. We want, what is the electron doing? How long time it takes for the electron to be emitted? What is the dynamic of the photoionization process? So we would like to go from the frequency domain to the time domain. How can we do that? What is missing? Well, missing is the phase. This is very similar to what you have in optics, in diffraction. We want to have the phase information, and this is what our attosecond technique give us. So missing the phase, again, an absolute phase, we don't care. What is important is the derivative of the phase or the delay. Physical interpretation is this delay of the electron wave packet as it is ionized. This is a measurement obtained in photoionization of xenon in the 4D shell. This is the 4D 3½ electron. So this is the time delay as a function of, or group delay, if you want, as a function of photon energy. The resonance peak at 100 eV, so we see half of the resonance. You see that we measure positive delays, in this case, a few tenths of attosecond. And this is the region of this giant dipole resonance. There is obviously something happening at threshold, which is due to a spin-orbit interaction, a spin flip at the threshold of this 4D ionization. And here you have a comparison between experimental result and theoretical result. This is very nice because now we can really do interpretation of the photoionization process and relate this to the dynamics of photoionization, relate that to some kind of effective potential that the electron sees as it goes out. In the case of the threshold, we have a rather broad potential barrier that traps the electron during a long time, 100 attoseconds, while in the case of the giant dipole resonance, you have a small delay of the electron, but the electron is going away rather fast. Now let me conclude by saying a few words about a new technique that we are developing, where we try to measure not only this wave property, but now a quantum state property. And the idea is that in most processes, actually you have a sum, an incoherent sum of different processes. So it's not clear at all that you can characterize this photoelectron with just a phase and amplitude. This is optics, but now we are doing quantum mechanics. So we had an idea to use not only this XUV radiation and the probe field with one color, but now two different colors, omega 1, omega 2. So we use now a bichromatic probe to probe the wave packet. This is the excitation scheme, very similar. We project, so we generate a wave packet that we want to characterize in blue, and we project it on a sideband. And just to illustrate a little bit the excitation scheme, I split now this photon, XUV photon into two. You see that we can go to the final state by two quantum paths. So same idea, with two quantum paths, we go to the same final state. I'm varying the delay between the probe and the pump. I get interferences and I get information on the phase. Phase, or actually absence of phase relationship. You can see that the signal, so this is the expression of the interference signal that you get, which now depends on the difference between the two frequencies of this bichromatic probe. You can see that this signal is going to depend on whether these two energy states, epsilon 1, epsilon 2, are going to have a phase relationship or not. In other words, they are going to depend on the coherences of the wave packets. So now here we can characterize, thanks to this method, the coherences of the photoelectron wave packet at these two energies, epsilon 1, epsilon 2, both the amplitude and the phase. So what we have created is really a tomographic technique to make a tomography of the electron wave packets, quantum state tomography. And we call this method Kraken. It's a very bad acronym. We use Swedish in order to get the K that we need. it's not my, I guess it's my responsibility, but it's not my invention. So it's a Swedish student. But anyway, we call this technique Kraken. This is an example of experimental results for different pairs. In order to do the tomography, we need to vary this pair of frequencies to span the wave packet. So these are examples of results for different omega 1, omega 2. And from this, we can plot the density matrix. So each oscillation leads to a subdiagonal of the density matrix, as you see here. So this is one example of result. We make a symmetry relative to the diagonal. So this is a density matrix where it's really energy, energy, and you have the population on this diagonal. Now, if we have that, then we would like to make a fit. This is called Bayesian optimization procedure leading to this result that you have here. This is very nice. It's a round density matrix. It's a pure state, nothing really new and nothing surprising. What is more interesting is, I should have, I'm going too fast now. Sorry for that. We can measure the purity, and it's very close to 1. Let's look at argon. In this case, the density matrix is not round, it's oval. Now everything is going apart. Oops. Yes. So obviously, in this case, we lose coherences at high energy. So what is happening? Well, what is happening is a spin-orbit interaction in argon. The ion can be left in different spin-orbit states, p1/2 and p3/2. So the electron can have different energy depending on the state of the ions. In other words, we produce an entangled ion-electron state in this process. And since we only measure the reduced density matrix, we don't look at the ion, we lose information, and the purity that we measure is 0.65. The case of maximal entanglement here is when the two distributions are completely separated, because then you know that if you detect an electron with a certain energy, then you know the state of the ion. In our case, and this would be 0.55, in our case, we have a small overlap, as you can see, and when the energy of the electron is in the overlap, then you don't know what is the state of the ion. This is the reason for this purity that we measured. It also tells you that we can vary the entanglement by simply vary the bandwidth of the XUV radiation. I'm going to conclude now. What is the next chapter in attosecond science? This field is growing into many, many directions at the moment. I presented some results in atomic spectroscopy. I think one of the challenges is to use these techniques to look at more complex systems, molecules, condensed matter. There are some industrial applications. And also, I present to you some ideas toward looking at quantum effects. There are also new sources of attosecond pulses, in particular using free electron lasers. This is going very, very fast at the moment. And these attosecond pulses have very different characteristics. They are much more in the X-rays, much higher energy per pulse, and often isolated. Now, I would like to conclude by showing some pictures, and this is for the young people here. I was awarded this Nobel Prize, I think because I was a little bit lucky, and I was part of an experiment almost 40 years ago. It's really a long time ago, and I kind of focused on the results of this experiment on this high-order harmonics. So think when you do your PhD or postdoc. At the time I was a young researcher, then maybe sometimes in the future, can take 40 years or more, you can be in this room. And what you have on the first, at the front here, the Nobel Prize laureate. So this is in 2023. You can see Pierre Agostini, Ferenc Rost, and myself. Physics is first. The Nobel wrote in his testament that physics should come first. And then you have chemistry, medicine, literature, and economy, which is not a Nobel Prize. And true, it's a prize. It was given by the Royal Bank of Sweden. It started in 1968, so much later than the Nobel Prizes. And maybe you will have the chance to receive a medal from the King of Sweden. After this ceremony, there is a banquet. It's a fantastic banquet with 1,300 participants. It's extremely formal. You have to stay during 4 hours, and you have no right to move. And maybe you will have the chance to sit close to the King of Sweden, which is a nice experience for a French person like me. And with that, I would like to thank my research group that you have here. And also on the right, this is the list of the senior people working with me in this group. Of course, we need to thank organization financing this research. And I would like to thank very much the University of Innsbruck and the German and Austrian Physical Society for inviting me. Thank you for your attention.